Mario here today. This is part of a series of webinars that Linea is organizing about LSST. Mario is the LSST project scientist for data management, and today he's going to present the concepts and plans for a platform that will enable users to do science with LSST data in the future. So Mario, it's all yours, please.
All right, thank you, Angelo, and thank you, Luis and Ricardo, for helping set all this up. I hope you can hear me. If you don't hear me at any point in time, please say so, and I'll try to adjust my microphones and things like that. So the thing that I'm going to talk about today is the talk is titled "Getting Ready for LSST: Services for Access, Exploration, and Analysis of LSST Data." But what I want to convey to you with this talk is what is it that LSST is going to deliver, and most importantly, the latter part of the talk is going to be about what services LSST is going to provide at the LSST data access centers. Those are really the locations where our archive is, to enable science, to enable access, to enable exploration, to enable analysis of LSST data. So I'll start with just a very, very brief introduction. You've heard about LSST already. You know about LSST, but it's good to summarize what the machine is. The way I think of LSST is it's not a telescope. It's not a camera. It's really a database of the sky. The LSST is a wide, deep, fast survey telescope. Beginning in 2022, it will repeatedly image the sky for 10 years. But it's really an integrated survey system. So the observatory, telescope, camera, and the data management system are all built to support the LSST survey. There's no PIMO, there are no proposals, there's no asking for time on LSST. So the ultimate deliverable of the whole system is not really a telescope or the instruments, it's the fully reduced data. And so the way to think about LSST, again, is that it's a facility that delivers data products and data access and analysis services to the community. In some ways, it's more similar to a space mission than it's to your typical telescope on the ground today. Where is LSST? Well, it's roughly right across the mountain from you. It's in Chile, in Cerro Pachón. On Cerro Pachón near La Serena. It is close to the Gemini telescope and the SOAR telescope. Here you can see an image from a couple of years ago when we started blowing up the top of the mountain to make room for LSST. Here's the photo of the site in 2015. That is now almost a year and a half ago. And here's the photo of the summit yesterday. So you can already see the LSST observatory taking shape on top of the summit. And if I actually switch to a camera that's mounted on the Gemini telescope, you can see the same thing from the side, and you can slowly see the telescope being built and the observatory getting created. If I zoom in furthermore, this is what it looks like. And so you can see the telescope support building on the left. This is where all the labs are. This is where some of the computing is going to be to support summit operations, recoding chambers, things like that. And on your right is where the actual telescope will be, the mirror, the camera, all of that. And so this is where we are now. And in about 2 years, this is what is going to be up there on the summit. So we are, and this is especially impressive to us who have been working on the project for quite a long time, we are just 2 years away from the observatory being close to complete and less than 3 years away from first light. So this is happening after decades of research and development and planning. We're actually building. The mirror is done. M1 and M3, it's being shipped to Chile. The mirror cell is being constructed, and the camera is being constructed as well. The camera consists of 189 science CCDs in 21 what we call rafts, so groupings of 3x3 sensors. It is a big camera, 3.2 gigapixels, 0.2 arcsecond pixels, 10 square degrees field of view, and a 2-second readout. That's probably the most impressive number about that camera, that we can get all those pixels read out in 2 seconds and move on to the next field. And of course, we're going to be using 6 filters, UGRZY, inspired by previous surveys such as SDSS and more recently Penstar, SenseTimeMapper, and others. This is just a brief introduction to the hardware so that I can put the software really in perspective and the data management system. The telescope and the camera, so the machine that does the actual observing, is in Chile. But virtually all of the data processing will be happening in the United States at the archive site at the National Center for Supercomputing Applications in Illinois. So we have 2, likely 3, high bandwidth network links linking the summit to NCSA, through which we will stream the data in real time. So we will have an image, every image that's been taken at LSST in Chile will be up at NCSA in less than 10 seconds. Headquarters site is going to be in Tucson, and there's also going to be a satellite processing center in at CCI 2P3 in Lyon, France, that's going to be helping us, or that's going to be participating in annual data release productions. So to go back to my first slide, when I said that LSST, you shouldn't really think of LSST as a telescope. You should really think of it as a database. This is an expansion of that statement a little bit. What is LSST from a scientist's perspective? Well, the way we think about it is in terms of data products. So we have 3 levels of data products. We have level 1, those get created every night, and that is going to be a stream of about 10 million time domain events per night, detected and transmitted to what we call event distribution networks within 60 seconds of observations. And I'll expand a little bit more about that in the slides to follow, but essentially the idea of level 1 data products is to quickly determine, to quickly find and alert the community to anything that's changed in the sky, so that if there's a particularly interesting event going on up there, that we know about it very quickly within about a minute, and that we can point large follow-up facilities to it. So there are 3 projects, for example, to build 30-meter telescopes. Those telescopes will want to have something to look at, and this may be one of the things that will give them a constant stream of interesting objects to observe. More likely for, let's call it, quote-unquote vanilla transient operations, you will want to have networks of smaller telescopes, where by smaller I mean 3 to 4 meter telescopes, so it's not really small, to be able to follow up objects that the LSST finds. But the key distinction here is that our level 1 data products are the ones that enable that. We find what's changed and we transmit that within 60 seconds to everyone who wants to listen to this stream. Another thing that's part of level 1 that happens at roughly the same time scale is the discovery of asteroids. So we're going to catalog about 6 million bodies, 6 to 10 million bodies in the solar system, depending on the model. And we're going to be finding them, essentially we're going to be discovering new ones every day throughout the 10-year survey. Now, if you are not interested in real-time follow-up, so if you're not trying to catch objects that change on minute timescales or daily timescales or monthly, level 2 products are likely going to be of more interest to you. Level 2 is intended to enable static sky science as well as science that really requires precision. So we call it systematics limited science. So these are data releases. If you worked with Sloan, with SDSS, or if you worked with DES, Dark Energy Survey, you're very familiar with the concept. every year, the LSST will take all of its observations. We're going to reprocess them. We're going to build coads. We're going to detect objects on those coads, and we're going to measure their properties. So that would generate, at the end of the 10-year mission, a catalog of roughly 40 billion objects. So split roughly half and half between stars and galaxies. So about 20 billion galaxies and 17 to 20 billion stars. These will be reobserved. So there's going to be around 30 trillion measurements of these objects. And most of them are going to be independently detected in individual epochs. So there's going to be 7 trillion sources, or 7 trillion independent observations of every single object that we'll have in the catalog. These will be accessible through online databases, and as I said, we will produce these annually, except for the first one. They'll be produced twice, except for the first year of data, where we will produce the first data release after 6 months and the second data release after 12 months, just to enable the science to start flowing as early as possible. The final piece of this puzzle is what we call level 3. We understand that level 1 and level 2 products are not going to satisfy everyone. They're not going to satisfy every single aspect of LSST science, or the science that LSST can provide. And that the community will want to build on top of both level 1 and level 2, adding value to it, adding value data products. And later in the talk I'll have some examples of that. So we want to make that easier, or make that as easy as possible to the members of the LSST community. One of the particular challenges with LSST is that the data set is going to be fairly large. So we're going to be collecting an order of 5 petabytes of data per year. And if one wanted to process or reprocess even a fraction of that, just getting it out of the data center and putting it somewhere at your institution may be a challenge. So what we want to do instead is to add some services, or add some computing, add some storage resources, add some database resources at the data center, so at our data access centers, so that you can take your code to the data access center. You can take an analysis of the data access center where it's next to the data, and be able to do some of that analysis and to create these added value data products. And then what we call federate them, which means make it easy to join them to the existing level 1 and level 2 data products that are already in the database. So this is what level 3 is about. It's not, level 3 products are not products that are developed by LSST, but these are added value products developed by the community that LSST hopes to enable by providing some resources at the data center for the community to do this. Everything I just told you is described in gory detail, but still I hope in a readable way in this document called the Data Products Definition document. Level 1 is described in section 4, level 2 and 5, level 3 and 6, and there's also something that I won't be talking about, which are data products for special programs, such as the deep drilling fields, which are described in this document as well. So I would really urge you, if you want to know more about what LSST is going to deliver in terms of data, this is truly the document to read. And it's been written, it's not a requirements document. It has prose. It really tries to explain what it tries to be more readable than a typical requirements document, I would say. And I would warmly recommend it to anyone who wants to understand more about LSST data products. Now, I'll go and take one step further in describing what's going to be delivered. And I'll start with level 1. So as I mentioned in that introductory slide, level 1 is all about enabling discovery and rapid follow-up of time-domain events. And the way we're going to do this is we're going to do real-time image differencing as observing unfolds each night. So what we're going to do for every image, we will difference it against a deep template that's been built out of imaging collected over the past year or so. That will give us, that difference will give us anything that's changed since the template was built. So on timescales of months or anything that varies significantly at timescales shorter than a couple of months, we will catch that way. Then we will measure the detected objects on the difference image, and we'll perform some measurements on the direct image. And we'll also associate those objects to pre-existing observations that are in the database and store them in the database as well. So what you will get is, for every source detected in the difference image, we will send out an event alert. Right now we're baseline on VIA event. It's almost certain it's going to be packaged as a VIA event. And we'll send out a VIA event within about 60 seconds of observation. That VIA event will contain the information that you need to decide whether this is something that's worth following up rapidly, whether this is a supernova that just blew up and you may be able to catch a steady shock breakout and things like that. So to give you a sense of how that works, this is, we capture the image. So I don't know if you can see my mouse on the screen, but we capture the science image, we difference it against the template, and we detect an object. That will happen roughly within 5 seconds of the receipt of the image up at NCSA. We will have that. Done. We'll have that differencing detection and measurement complete in about 50 seconds and stored in an internal data store. And then we broadcast alerts within 60 seconds. So if you want to really do this follow-up, you will subscribe your VIA event client to the LSST data stream to receive the data in real time. If you don't care about real-time follow-up, but would like to understand at the end of the night what has happened, we will also be storing these data in a level 1, what we call level 1 SQL database. So within 24 hours, you'll be able to query this database same way you're used to querying, say, data release databases on DES or SDSS to see whether there's anything that's changed in the previous night and perhaps something that you might want to follow up in subsequent nights. At the same time scale, we're also going to make images available from each night. So you'll have access to LSST data effectively in real time, to LSST image data, raw image data, as well as the processed catalogs. And at the same time scale, we're going to be updating the Solar System Object Catalog as well. So you can see that everything here happens within 24 hours or so, with the alerts being very aggressively pushed out within just 1 minute to enable these rapid follow-up science cases. Now, to enable those kinds of science cases, one of the things, if you have a big telescope and you're waiting for LSST to send you something interesting, you need to understand, you need to know whether it is interesting, or you need to decide whether it is interesting or not. So to do that, the LSST needs to give you some information about the object, and that information needs to be packaged with the alert that LSST will be sending out. So the question is then, what will LSST send out in each of these alert packets within 60 seconds? And roughly the answer is everything we measure or know about that object, either now at the point where we detected it, or historically, so previously, if that object was detected before. So here's just a quick summary or an excerpt of what that will be. The details are in the data products document, but roughly for each object detected in the level 1 data stream, we're going to measure PSF photometry. We're going to give you position. We're going to characterize its shape. We are going to also give you cutouts, so small, roughly 30 by 30 pixel cutouts of the object and its surroundings from the actual difference image and from the template image. So this allows you to for one, actually view the object and visually confirm that it's not an artifact, but also to run your own algorithms on those postage stamps to understand what the object is. We'll also give you a time series of all previous detections of the source. Because for performance reasons, we're not going to do that for let's say 10 years worth of data at the end of the survey, but only for the past trailing year. But again, this is light curve information that should give you this light curve data that should give you a lot of information about whether this is an interesting object for your science case or not. And we'll also compute various summary statistics, or what we call features, on those time series. A standard example there is period. So we're going to give you what the estimate of the period is for this object, some features for that are better suited for studying quasi-periodic objects, and in a sense, values that allow you to understand, classify what this object is without having to go through the time series and do this computation on your own. And again, as I said, the goal here is this is a lot of data for each packet. Each packet is going to be in an order of a few tens of kilobytes. But the goal here is to transmit nearly everything LSST knows about any given event so that we enable downstream classification and decision making without the need for you to call back into LSST databases. Because if you need to call back into LSST databases, this will introduce extra latency, and if you're trying to catch objects that change on timescales of minutes, then seconds really matter. The other reason we like to do that is very practical, which is that we're expecting a very high rate of alerts, approaching something on the order of 10 million per night. So if for every alert, your system, your follow-up system, launched a query back into the LSST database, that would really overwhelm the LSST system and would not get you the data you need in time. Now, because of that high rate, so I said roughly 10 million events per night, this is actually going to be a pretty sizable stream. We're talking about hundreds of gigabytes of data being sent out each night. And we realize that not all science cases are interested in everything. So for example, if I'm interested in fast-moving asteroids, then all objects I care about are those that trail, that have evidence of trailing in the image. So given that, what we've understood for a while is that we need to provide some kind of a facility to enable our downstream users to only receive a subset of alerts that match their scientific interest. For example, potential supernova candidates, available stars, and moving objects, and not everything. And to support selecting such subsets, what we'll do is we'll provide what we call an alert filtering service. The way this service will let astronomers create simple filters that limit which alerts are ultimately forwarded to them, but really the way to think about this is that it's the equivalent of querying a database, except you're just querying a data stream. So again, bringing this back to something that we're all familiar with, like DES or SDSS. The way you access those databases, you go and write a SQL query, and then the database goes away and returns you the objects that only match what's written in the SQL query. What this filtering service will do is it will let you write a filter that, because the data doesn't exist yet, that will be put in place. And as the data is coming in, it will be matched against that filter, and only the things that you care about will be forwarded to you. So it's kind of analogous to querying, but just for real, not for databases, but for data streams. And these filters will be possible to specify using something like either an SQL-like declarative language or short snippets of Python code. This is, I need to put a caveat here that we are currently working on exactly how to implement this. So this is the current thinking, and it may be subject to change. But to give you a feel for it, here's what a Pythonish filter may look like for that will only forward you never before seen events within 2 effective radii of a galaxy. So maybe the goal here is to find supernovae in nearby galaxies or supernovae in external galaxies. So I have just a simple Python function that gets passed an alert packet, and then I make a decision based on what's in the alert packet, whether it should be forwarded to me or not. These filters all run at the LSST data center, and we will let the users set them up and have the packets that match the filters passed on to them. So how does this work with what are called via event brokers and networks? The answer is it works really well. We anticipate that in addition to what we are putting together that allows you simple filtering of LSST data, that more advanced public filtering services via event brokers will be established by the community. And these may provide advanced functionalities such as cross-correlation of LSST alerts with external catalogs or with other alert streams, classification engines. So one of the things that LSST will not do is classify objects. That is, we will not tell you this is an RR Lyra. We will tell you this object has a period of 0.8 days and has a light curve that looks like this, out of which you can infer that that is an RR Lyra. But these kinds of public brokers may enable you to do to attach those kinds of classifications to LSST events. Extensive annotations of alerts, coordination of follow-up groups, incorporations of other contextual information. And so one of the things we're doing is, as I said, this functionality on this slide is something that LSST is not providing. So we are encouraging the community to self-organize and develop such alert brokers and networks. And so far, there, in the US at least, there's a project called Antares, led by a group at NOAO, that is building this kind of a system. And we're looking forward to sending all the LSST alerts to Antares and enabling our users not only to connect to us directly to LSST, but perhaps to connect to Antares to receive and filter alerts with even more information attached to them than they would get only if they only connected to the LSST data center. The other thing that Level 1 is going to deliver are solar system objects. Solar system objects will be identified and linked together based on their compatibility, of their observed positions with motions around the sun. So basically, the way how you determine something is a solar system object, or which roughly translates to an asteroid. The way you determine whether something is an asteroid is you observe it multiple times, and then you notice that those observations all lie on a trajectory that is consistent with a Keplerian orbit. And we are developing codes to do that. For those of you who work with asteroids, you may have heard of MOPS, Moving Object Processing System algorithm. We have an advanced prototype of that code in hand, and we plan to identify and link observations of solar system objects. By the end of the survey, we expect between 6 and 10 million new asteroids discovered by LSST with measurement of their orbital elements and photometric properties. And interestingly, for planetary defense purposes, we expect to detect and provide orbits for more than 60% of all NEOs brighter than age 22, which translates to roughly 130 meters in size, 130 meter object in size, and NEO stands for near Earth object. And those objects are interesting because if one of those collided with Earth, it would cause continent scale destruction. So it's very important that we eventually discover them and catalog them all, so we can know whether there's any one that's on a potentially problematic orbit that would take it close to Earth, including potentially colliding with Earth. So these will all be done within 24 hours of orbit determination. As I said, to determine that something is an object in the solar system, you need to reobserve it multiple times, roughly over the period of time of about 2 weeks. But once we've collected enough observations, we can determine an orbit, and then we make it public within 24 hours or so. So this is level 1. This is what you get immediately, within a day, within 60 seconds a day. If you care more about depth and high precision astrophysics, then what you'll care about are data releases. So level 2 data products. Level 2 data products will come annually. They'll consist of well-calibrated, consistently processed catalogs and images. Again, this is very analogous to what you've been used to seeing with DES or SDSS or WISE or any other modern survey for that matter. As I mentioned, they'll be done annually except for year 1. We expect to do 2 data releases in the first year of data, for the first year of data. And for each data release, we will reprocess all the data from the beginning, from scratch. So that means that each data release is going to benefit from all the improvements and new features added to the software to that point in time. And as we know, software keeps evolving. We're finding new ways to measure objects. We're finding new ways to characterize objects with more precision, more accuracy. And so having the ability to reprocess everything with the latest versions of code is really crucial to extract most out of the data set, out of data set like the LSST. Projected catalog sizes are going to go from something on the order of 20 billion objects to 40 billion objects, 20 billion in DR1 to 40 billion in DR11. And the interesting thing here is that DR1 will be based on only 6 months of data, while DR11 will be based on 10 years. But the increase in number of objects is only a factor of 2, which you may find curious. But part of the reason for that is that LSST is deep and the galaxy is finite. So we actually observe most of our stars very early on. So even in initial data releases, you will get a lot of information. You don't have to wait for the 10-year data set to get a very good galactic catalog. You'll get that at the end of the first year or the first 6 months. So there's lots of science that will start coming out of this telescope, off this telescope immediately, as soon as we're on the sky, as soon as we publish the first data release. What's going to be in this archive? We're going to have process visits, so reduced images, images with instrumental signature removed, background PSF, 0 point WCS determined, so you'll be able to download these and do further science with them. We'll also have coads, deep coads across the entire survey footprint and multiple flavors of those coads. But what I think most people are going to use are catalogs, partly because of the scale, but mostly because of the ease of use. We're going to have catalog of sources. These are sources detected on every single exposure. We're going to have catalogs of objects. So these are objects that are detected on coads and then characterized with a method called multifit, and catalogs of force sources. So for each object we detect on coads, we will go and photometer it, and on every single image that was on every single exposure, every single visit that was taken in that area of the sky, so that you can create light curves and that you can do further or different kinds of characterizations than you would only on the coads. So here's one more slide, a little bit more in depth on what that catalog is going to have. So when we say we're going to detect objects and characterize them, what we typically mean is, for one, we will do things such as aperture magnitudes and PSF magnitudes. But I think the more interesting measurements are going to be models that we're going to be fitting to every single detection. So the two that we'll be fitting to every single detection are a moving point source model, which is intended to represent stars, mostly stars. And so for every object in the LSST database, we will see whether it's consistent. We'll fit a model and see whether it's consistent with a source in the Milky Way that's PSF-like and that's moving. So that will give you position of the object, its own epoch. It will give you its proper motion, and it will also give you photometry. And for galaxies, we'll fit a double Sursic model. It's essentially a bulge plus disk model. And on the right in this slide, bottom right is a visualization of what this fit looks like. So for every object out there, and this is particularly useful for galaxies, you will have a characterization of what the shape of that galaxy is and what the object looks like in terms of these double Sursic parameters. Now we're also going to do non-parametric object characterization. We'll compute centroids, we'll compute adapted moments and elasticity measures, aperture fluxes, Petrosian magnitudes, chrome fluxes, chrome radii. We're going to do all these per band, and they'll all end up as columns in the database. Another important thing that we're going to deliver in these catalogs is seeing independent measure of object color. This is actually very non-trivial. It's easy for stars, which are point sources, but for galaxies, even the definition of color is difficult when you take into account the fact that there may be color gradients in the galaxy and that there's also seeing, atmospherically induced seeing that changes. So in some cases, depending on your seeing, or if you're not careful, depending on your seeing, or if you're not careful, the measured color may depend on your seeing. And that is something that, of course, is detrimental to science, and we will debias that and provide seeing independent measure of object color. And finally, although these are products produced in data releases, there's still a ton of information there. So we will compute all the variability statistics that we also compute for level 1, period, flow, electron moments, etc. Add those to the columns, to properties of each object in the database. So if you care, again, let me take an example of RLIRA stars. If you care about RLIRA stars, you'll be able to select a good candidate set by just writing a SQL query to filter on period and on the shape of the light curve that's consistent with RLIRA. So all of this will be delivered once a year, except for the first year of data when we're going to deliver it twice a year. And all of this is going to be in SQL databases the same way that we're used to working with, for example, SDSS or DES these days. So this, I hope, gives you an idea of what level 1 is going to deliver, what level 2 is going to deliver. And for the final 15 minutes or so of the talk, I'm going to talk about what level 3 might be and what services we want to provide to enable you, the community, to create these added value data products and also to do analysis of LSST data close to where the data is at the LSST Data Access Center. So as I mentioned in the introduction, level 3 data products should really be called added value data products. I actually personally dislike the term level 3 because it's meaningless without a definition. Added value data products is a bit better understood because we've had these for SDSS, and I think we have them for DES as well. So these are products created by the community that we have not, that we do not deliver, that the facility itself does not deliver. And these may enable science cases that are not fully covered by what we generate in level 1 and level 2. And I have just a couple of examples here of things that level 1 and level 2 data products where we don't have a particular data products in level 1 and level 2 to enable specifically these kinds of science cases. So one example may be a catalog of supernova light echoes. All of our data products are very much geared towards detecting and characterizing localized objects. So objects that are either stars or galaxies, if there's something diffuse, we will not see it. It will not be in our catalogs. It will be in the images. So light echoes are one example. Characterization of diffuse structure is another. Then extremely crowded field photometry. We do not plan to build purpose-built crowded field codes to process all the LSST data. Our codes are likely to fare reasonably well in crowded fields, but definitely not. But with a specific crowded field code, it's likely that you might do better. So this may be a good added value data product. And then you can come up with custom measurement algorithms. For example, if you're interested in interacting galaxies, if you're interested in galaxies that don't look really like double Sirsic combinations, you may come up with a different ways to characterize them, and you will want to run that. So these are all various science cases that may spur the community to generate new data products on top of LSST data. And we want to make it easier for you to create and distribute those. So the way we want to do that, or the way we're planning to do that, is in 3 ways, really. One is by enabling limited end-user analysis and processing at the LSST data center. What I mean by that I'll describe in just a second, but the gist is we have some computing, storage, and database resources set aside for the use of the users, for the use of the community, to do analysis at the data center. Think of it as our own private cloud that lives next to the data, and therefore has fast connections to LSST databases and LSST data stores. We will give you user databases and workspaces as well. So those of you who have used SDSS will recognize this as quote-unquote MyDB. So a place in the database where you can store your catalogs that you've created. And indirectly, we'll enable this by making the LSST software stack available to the end users. Now, the primary reason why we're making the LSST software stack available, the code available, is to enable reproducibility and to enable insight into algorithms. But this is a fairly well-designed stack, fairly well-designed software product that's modular, that can be built upon. And one of the things that the community will be able to do is to take our code, to modify it where it needs to be modified, or add features that they need for their science case, and then just rerun it. And therefore, I mean, through doing this, we're hoping to save some time and effort to the community, because a lot of the work in building astronomical pipelines goes into what you might call straightforward but tedious issues within the pipeline, and the actual science content may be in only a few small modifications. This way, you can jump straight to those few small modifications and build on top of the code that we provide. And another reason for level 3 is, or another thing that we envision happening with level 3 is, if there are level 3 products that turn out to be very interesting to the broader community, and if the owner agrees, then LSST in its operations may take them or may adopt them and start producing those and essentially add the particular level 3 data product to level 2. And so in the next release of the level 2 data, you would find that level 3 product as well. So this is, I think, one of the ways how level 2 products will evolve, by looking at what the community is doing, discovering things that are particularly useful to everyone, and then adopting them for level 2, again, with the owner's permission. Now, how do we enable all of this work? So how do we enable you to access, explore, and analyze level 1 and level 2 data and to create level 3 data set? We do it by providing a number of LSST Data Access Center services. We're essentially trying to build a platform on which to do science in the LSST Data Center. And this is what that platform will look like. We'll have the telescope, we'll have the data stream, we'll have the data set, and a number of services that the user sees. And I'm going to go through each one of them in the remaining couple of minutes to give you a sense for what it will feel like to access the LSST archive and to manipulate the LSST data. So LSST's key deliverables are the data, level 1 and level 2, and a way to reach it. So the way to get that data and turn it into science. For data streams, for alerts, it's the ability to ingest view events. For databases, it's this querying capability that allows you, or for level 2, it's a querying capability that allows you to get to the subset. So to make those data products, level 1 and level 2, available and useful to the community, we, the project, are building 2 data access centers, one in the US and another one in Chile. And these will expose the LSST data to the data rights holders through a number of what we call data access center services. The most common way how people will access LSST data will be through a web portal. The web portal to the archive will enable browsing and visualization of the available data sets in ways that you're already accustomed to at archives such as URSA, MAST, or the SDSS archive. We do plan to add more interactivity and more visualization capabilities to this portal, but roughly, if you've been to URSA, if you use the WISE data set, this is very similar to what's already there. Through this portal, users will be able to view LSST images, to query the data, request subsets, construct simple plots, generally explore the data sets. The goal here is to enable you to interact with the data set, to discover whether it's interesting for your science case, and to get the subset of the data required for your science case. And we have a very advanced prototype of that already. We're basing the portal on Firefly technology out of IPAC. Firefly is already deployed at URSA. It's serving WISE data. And you can see the kinds of things that you'll be able to do, you're already able to do here, that we will be able to do with LSST. So you'll have the capability of visualizing an image, get all the sources that are in that image, create related color magnitude plots and color plots, select subselect sources into color plot, have that subselection be reflected on the image that's being displayed, look at various histograms, and those kinds of services. So I don't think there's anything very surprising in there, because this is really what's state of the art today, and we're going to push that one step further in creating this portal as the first point for the users to interact with data. Now, as you're working in this portal, and as you're making selections by essentially writing SQL queries and then clicking on images and clicking and selecting regions in plots, invariably at some point you get to a point where there's not enough expressiveness in just the web portal to continue, and what you would really like to do is to take that subset, take that data set that you've subselected, and start writing code around it, start writing analysis code, whether it be in IDL or Python or whatever you use. Now, we're not going to be able to support any kind of analysis system. I mentioned IDL, for example, but what we will support is Python, or more accurately, we'll support Jupyter notebooks. So the way we envision this is you may start your work in the portal, and at some point you narrow down your data set to something where you really need to start writing code around it. You push a button, a Jupyter notebook pops up that has that data set imported, or that has access to that data set subset. And then you continue using that Jupyter notebook the same way you would do on your laptop if you had all the data on your laptop. The difference here is that the Jupyter notebook is actually running at the LSST Data Access Center and has fast access to the databases that are in there. This is very similar in nature to efforts such as SciServer at Johns Hopkins, if you've seen that, or if you're using it, to Jupyter Hub deployment for DES at NCSA. So we're trying to leverage what the community already, how the community is already getting used to using these tools, and also the knowledge that's being collected by these experiments and by these implementations for surveys before LSST. And as long as we're giving you a notebook, we also have to give you some computing, some storage, and some personal database capability. We call the combination of the three of those the user workspace. And the crucial thing there is that you can save data to these databases. You can save images, for example, to your storage allocations. You can use the computing facility to run some processing on both of those. And no matter which way you access it, whether you access it through Jupyter Notebook, whether you access it through the portal, or whether you access it through VO APIs, say using Topcat, you'll always see that same workspace. So you can think of that as your remote database / storage / computing drive, quote unquote, or allocation at the Data Access Center. How much of that is going to be available? Well, at the beginning, this cluster will start at roughly 2,400 cores. In terms of computing, we have about 3 petabytes of disk space in the US, shared by on order of 1,000 users or so. So it gives you an idea of what kind of quotas you're going to have to play with. And database storage will be an order of 2 petabytes. And this will not let you do large-scale analyses at the LSST data center. So this will not let you, for example, reprocess the entire data set going back from the pixels. But for a large majority, I believe, of science use cases where you're dealing with the catalogs, where you would like to visualize and do some analysis on catalog data, this may actually be sufficient to do all of your science at the data center. And if it isn't, it will be sufficient to begin doing that science to the point where you discover you need more resources and then go apply for more resources, either at your home institution or resources adjacent to the LSST data access centers. And I'll say a little bit more about that in a second. The final piece of this puzzle is that we will also be making the source code of the LSST data processing software available, as well as configurations used in processing. And I already mentioned this when I spoke of level 3 products. The primary idea is for this to enhance reproducibility of LSST data products, as well as provide source code level of insight. But also having the source code may enable the community to extend and apply it to projects beyond LSST. There are already some efforts to do that on agency survey data and or in CFHTLS. And having the source code, I think, is going to be very useful to do science with LSST. So putting it all together, this is the slide that opened this section. You can think of this as the LSST science platform, really. The services that are going to be offered in the LSST Data Access Center, the portal, which will be used by the majority of people, the notebook for more advanced analysis, and then the associated computing storage and database resources, as well as the source code if you really, really want to understand or build upon on the data processing algorithms that LSST has utilized. So for my essentially final slide, here's some thinking about how we will work with LSST data. So 2022, 2023 comes along, and how do people interact with this? I suspect that most users are likely to begin with the web portal just to become familiar with the LSST dataset and query smaller subsets for quote-unquote at-home data analysis. Some may skip the portal and just use the tools they're accustomed to. We're going to be exposing VO-compatible APIs, so things like Topcat, Aladdin, or AstroPy will work perfectly well with their archive, and you'll be able to use those to access the archive as well. Beyond that, some users may choose to continue their analysis at the DAC by utilizing the resources we have set aside there. So the Jupyter notebooks will be, we're setting aside about 10% of all of our storage and computing resources. That starts at about 20 teraflops, goes up to about 100 teraflops by the end of the survey to enable this. We'll use this to power Jupyter Hub type remote analysis environments, so Jupyter Notebook. And it's quite possible, as I mentioned previously, that a large fraction of end-user science may be achievable this way, end-user analysis. You should think of this as us giving you your own 20-core machine next to the data center, next to the LSST data to do analysis on. And I think it's a quite reasonable environment, given that today, for example, for my own science, I mostly do it on my laptop. Having my laptop close to the data is really what I will really need in the LSST era. And for users who need even more, they may be able to apply for more resources at adjacent computing facilities. For example, US Data Access Center is at NCSA, and it's likely that significant additional supercomputing capability will be available at the same site. So for example, literally next to our machine at NCSA is right now the Blue Water supercomputer that is already a petaflop machine. In the 2020s, it's reasonable to expect that there's going to be much more computing there, and you'll be able to apply to that through the usual NSF process of applying to computing resources. And finally, data rights holders may also build their own DACs or computing facilities to support larger scale processing, reusing our software to the extent possible. So you can imagine building a DAC in Brazil. You can imagine, for example, a large collaboration may import the large subset of LSST data to a different data center, different computing center, and do reprocessing from scratch. And what we hope to do here, I mean, this is all beyond the project, but we can help there by making our software available, and that's what we're doing, so that some of that software that we're using internally to do data processing can be reused. So I will end with this slide. LSST will start operations in 2022. These are the kinds of services that we'll make available to the users. These are the kinds of data products that those services will expose, level 1 and level 2, and I hope you'll find them useful. So I'll stop here and take any questions. Thank you.
Questions?
I have questions.
Please, Luis.
Mario, I mean, of course, you know, you have a very open-ended kind of problem that you have to face. You have to serve an entire community. But for instance, in our case, I mean, one thing that we have been struggling a lot is that if you want to do some statistical analysis, you have to deal with other kind of problems. For instance, the lack of homogeneity, you know, across the sky, so you have to build masks, you have to compute the depth maps. Also, you have to make sure that you have a star-galaxy separation, photosys. I mean, how do you guys imagine that being done? Or that's out of scope, outside scope?
So for actually, we are going to be the depth maps are one of the products that we're going to deliver, and the masks. So some of that you're going to get with the survey. Now, of course, if you know for a particular science case, you may want to build your own with your own criteria. And there, I think this level, this computing allocation in the data center may help you. So you could write codes that query the LSST. Let's say you're doing it off catalogs. You can write codes that query the LSST database for the particular kinds of objects that that you care about, and then in parallel stream the results of those queries to nodes at the DAC that are doing the computing. I think it's no different in many ways than the way you would do it with DAS now, except that there may be sufficient capacity at the LSST DAC to do it server side. I know I'm not being very specific, but I don't think there's a good generic answer there. It really depends on the scale of the problem you're facing.
Yeah, and also, I mean, one issue we had to deal with is also the parallelization scheme, right? I mean, it's not obvious that you just run something. You have to make sure that for different science you want to parallelize in different ways. So we had problems also in serving the data. We had to go to Hadoop, things like that. So we went way beyond what we expected to do. And I was just wondering how you guys are going to deal with that, or if it is a better better strategy to actually develop your own, not a full DAC, but something at home that you can actually do it more customized for your science.
Yeah, I think that we're definitely not expecting everything to be done at using DAC resources. And there may be cases where you really want to download a large subset of the data, load it into Hadoop-style environment, and run your processing there. And I think that really will depend on your use case. So what I try to do with presentations like this one is to explain what will be available, and that is computing resources on the order of 2,000 cores and an IPython type interface. So this is kind of geared towards smaller end-user analysis. I think if you want to go beyond that, and if you cannot do your analysis using those resources, then yes, you may want to have a, say, Hadoop version of the dataset running somewhere outside of the DAC or the official LSST DAC.
It's not going to be impossible to download the catalogs, right? The catalog.
Oh, no, certainly. Yeah, we will make everything bulk downloadable. That's one of the very strict requirements. Sorry, go ahead.
No, go ahead.
No, what I wanted to say is it's true that the LSST dataset is big, especially when you talk about images. But the catalogs themselves may not be as scary as we think they are in terms of size, right? Because our catalogs are also an order of petabytes, but a lot of that comes from hundreds and hundreds of samples we take to characterize posteriors for shear measurements for dark energy. Most science cases probably will not care about that. If you narrow down the subset of the catalog, the subset of columns, to the columns you care about for your science case, actually the entire catalog may reduce to something quite manageable for your science case. It may reduce to tens or hundreds of terabytes. And again, hundreds of terabytes may seem scary today, but in about 5 or 6 years it won't be. So I would be surprised that if many people actually go along, do this bulk download, take this bulk download route, and just download large subsets and then play with them at home. That's a perfectly valid thing to do. And people, we're kind of like squirrels. We like to take the nuts and take them back to our holes, astronomers. And I suspect that that's what's going to happen as well. There's nothing wrong with that.
All right. Thank you.
Questions?
I have another question.
Okay.
It's Juric. Mario, if we consider single images and objects fainter than red magnitude 22, what accuracy in astrometry and position you can expect to these to those objects?
Oh, that is a number that I should know, but unfortunately I don't. It is so an interesting. I know where to find it though. So there's a plot showing astrometric accuracy, predicted astrometric accuracy versus apparent magnitude in the LSST science book. And one number of interest is that our accuracy and Gaia's accuracy, so Gaia's accuracy at their faint limit, which is roughly 20.5, our accuracy and Gaia's accuracy are the same. So if you look at those two curves, I remember from the plot, they kind of smoothly continue onto each other. So I can look this up later and give you that piece of information. But if you Google for LSST Science Book and look at the chapter on astrometry or proper motions, you will find exactly the plot that you want to see.
Okay, so basically, you're saying that you are around few milliarc seconds to sub-milliarc second to those objects.
No. It's more than that. But that's what I'm saying is, I mean, Gaia's accuracy drops dramatically as it gets to its faint end, and it becomes roughly equivalent to LSST's accuracy at that very faint end. It's more than milliarseconds, though.
Okay. My question is, suppose that I, for some reason, decide to reprocess a specific CCD for solar system object. So let's say I have an object of interest in the LSST catalogs. Is it possible to, knowing the object or its position and date of observation, to identify and locate somewhere the CCD where the observation is?
So the question is, if you have ephemerides of an object, can you map that to essentially pixels on the CCD?
Basically, what I think you provide a list of known objects, of known positions of solar system objects you observe. And if I decided to, for a given object, to reprocess the same CCD, would it be possible to go directly and take the CCD where that specific position is?
Yes, certainly. One of the things that we're providing is we will let you, we have something called the image access service, or the cutout service, where you'll be able to specify the location of the sky and time when you want the image, or a range of times that you want the images for, and we'll return you the images. So for example, if you wanted to do that for a particularly known asteroid, you could easily compute ephemerides for the asteroid at times of observations of LSST visits, and then just request those visits through that service, and it's going to, you'll be able to write a little Python script to do that.
Okay. Thanks.
I have a question to Katas here. So, do you plan to measure photometric redshifts on some level 2, level 3?
Yeah, so we have a requirement to compute photometric redshifts based on a still-to-be-selected algorithm from the literature. So what that means is, I think with the help of our science advisory committee and the project science team, we will decide on an appropriate algorithm that essentially transforms the colors that we have in the database into photometric redshifts. We'll run that and we'll provide that in the database. So as part of level 2, there will be columns with photometric redshifts. Now, photometric redshifts are, I think, how best to measure them is really an unsolved and unsettled question. And so I expect that there will be level 3 products as well, computing photometric redshifts using different algorithms, and you'll be able to both create and use those as well. But there will be something provided by the project, or that is the plan right now.
And I'm sorry if I missed it. The DAC is accessible to anyone, or?
They are accessible to the holders of LSST data rights. So that means the U.S. community and Chile and the international contributors. And I understand there's a group of PIs in Brazil who are also in that category. Beyond that, right now we don't envision that LSST the LSST provided DACs are available to others.
Okay.
Mario, Angelo here. So you mentioned that some of the level 3 data products would migrate to level 2. Does that mean that they will be released together with the level 2 data products each year?
Yes. So it means we would effectively adopt them and turn them into, treat them just like we would any level 2 data product.
So, and there is any requirement for those level 3 data products to be reproducible?
If that happens, so if we decided to adopt a level 3, turn a level 3 data product into level 2, we'd effectively do it under the same rules for level 2 data products. We would potentially rewrite the code to make it maintainable, to make it reproducible, to make it public. Someone can create level 3 code in IDL, for all I know, but we cannot run that in level 2 pipeline. So if we decided that this is really useful and that we should really do this as part of level 2 for the entire community, then LSST project treats it as level 2, and including with all the support and everything.
Right. Okay.
I have an additional question here. I mean, it was in our plans, and in fact we asked for funds to do that, to actually transfer or implement here some version of QServe to get our hands into this technology. Is it mature, Mario, or is it still under development?
It's still under development. I think there are deployments elsewhere. There's a group in France, the deployment of QServe, but I think it's still very much a project that's under development, and it would take effort. So I would say, I'm not discouraging you, I'm just saying it's not the sort of thing where there's even documentation that's very detailed about how to install it. There is some reasonably good documentation, but expect it. I would hesitate to go into something like this without a postdoc devoting their time to it at a level of a couple of months at least.
And what are the plans for the science verification period with the full camera? How long? I mean, are there plans? I mean, how long do you expect that to be? Because when you guys talk about 2022, I mean, science verification with DES was fantastic. I mean, it produced lots of papers. So.
So the commissioning plan, our science verification is part of commissioning, and the term is slightly overloaded because I don't think what DES thought of science verifications is the same thing that we're thinking of as science verification, or maybe DESI is thinking of as science verification. So the way we're thinking of science verification is where we characterize the performance of the system and potentially slightly optimize some areas of the system, or some parameters in the system to make the science performance better, but it's still not designed to do science. So that period should take, with the full camera, should take on order of 6 to 8 months. I hesitate to say more than that because literally 3 offices down, we're currently having a workshop to work out those details of the commissioning plan for LSST. And that will,
Fair enough.
the time to ask that will be actually in January and February when that commissioning plan is done and reviewed.
Okay, fair enough. Thank you.
More questions? If not, so let's thank Mary again, and thank you very much, and see you later.
Thank you,
Thank you,
Tim.
Mario.
Thank you. Thanks, Angela. Thanks, Luis.
Mario,